Alright, so let's go ahead and work a example problem to try and show how this works. And if you want to work ahead, go ahead and you can pause right now and try and use the tables to see if you can solve for what the region and specific internal energy. Otherwise, just follow along and we'll work through how one of these problems works. So we have temperature and pressure, so we're looking at a rule 1. So we need to find first what region it's in. So to do this, we're going to use our pressure table. So we're using table 11. And we go in at the pressure that we had of 300. Now we see here, granted, and notice we had 0.3 megapascals. 0.3 megapascals equates to 300 kilopascals, and this table is on kilopascals. So we have 300 kilopascals. At 300 kilopascals, our saturated temperature is 133.6. Well, we have a temperature of 200 degrees Celsius, so that's higher than our saturated temperature. If it's higher than your saturated temperature, as you can see right here, so if our temperature is higher than our saturated temperature, well, then that means we're over here on the line, on our constant pressure line, so we are in the superheated range. So we're superheated. So we go to our superheated tables and we look at the superheated tables to find pressure at 300. So in that sub-table of pressure at 300, we're going to find our temperature of 200 degrees Celsius here on the right side. If you're on the left side of the book, it's going to be on the left side. If you're on the right side of the page, it's going to be on the right side. And then we find our internal energy, and we see it's 2,650.7 kilojoules per kilogram. So that is our specific internal energy at that state. So let's go ahead and do another one. So now we've got, again, we're at 200 degrees Celsius, but now we're at 4 megapascals. So again, we're going to that pressure table. We're at 4 megapascals. So we see our saturated temperature is 250.4. So now our temperature is less than our saturated temperature. Well, let's go ahead and look at that diagram. At a given pressure, if our temperature is less than our saturated temperature, well, now we're in the compressed liquid region. So because of that, we're going to go ahead and use the compressed liquid rule. So we got to use table 10. We can't use table 11. You've got to use, look for the values at that temperature, because pressure is no longer as important as temperature when you're in that liquid form. Okay. So we go to table 11. It should be table 10. We go to 200 degrees Celsius. And we look in the saturated liquid column because it's compressed liquid, so we know it's going to be a liquid. And we get 0.0011565 meters cubed per kilogram, and that's our specific volume. Alright, so for the third one, let's look at, we're given pressure of 0.2 megapascals, and this time we're given a quality of 0.8. Well, if they give you a quality, quality only exists in the saturated mixture region. So we know right off the bat that this has to be in the mixture region. So we're going to use table 11 because we only have pressure, we don't have temperature, and we have quality. So we go to our pressure of 200 kilopascals, and we're trying to find enthalpy. So we're going to look here at the enthalpy values. We have enthalpy of our liquid, and we have the enthalpy of evaporation. So we're going to use the formula that from our quality relations of table 4.1 on page 4-9, which states that enthalpy is equal to, at our state, is going to be equal to the saturated liquid enthalpy plus our quality, which happens to be 0.8, times our enthalpy of evaporation, which is, in this case, 2,201.9. We plug that in, and we get 2,266.22 kilojoules per kilogram. Okay. Now, for the next one, we're going to show how to compute a value using interpolation. Interpolation is how we can find values assuming a linear relationship over a short enough distance. So you probably used interpolation previously in math courses, so it may be a little rusty, so we'll go through this pretty slowly. We can use interpolation to find values between liquids and vapors, which is basically what the quality relationship is. It's an interpolation between those two values. Or we can look at it between different rows of data in one of the saturated water tables. So here we have a problem where we're given 610 degrees Celsius temperature and a pressure of 0.5 megapascals. So we go to our saturated mixture region table and look at pressure. And we have at 500 kilopascals, we have a saturated temperature of 151.9. Well, we had 610 degrees Celsius is our current temperature, so that's well above our saturated temperature, so we know it's going to be superheated. Again, here's the chart. You can see if our temperature is greater than our saturated temperature, we're in that superheated region. So we're going to use table 12. So using table 12, we know pressure is 500 kilopascals. We have a temperature of 610, so it's between 600 and 700. And we are trying to find our enthalpy. So we're going to take the values at 600 and 700, and the low temperature is going to be 600, our high temp is 700. And this is our low value for enthalpy and our high value for enthalpy. So we're going to do a linear interpolation, where we're going to say that for solving for enthalpy at 600 degrees 10, we say that if we were to interpolate between these two values, we can say our low value, our change between our actual and our low value, will have the same rate as our change of temperature over enthalpy. We'll have the same rate change as our change from our high temperature to our low temperature over our enthalpy high to enthalpy low. So how does it look in numbers? You put your actual temperature in for the state, 610. We put our low temp. We divide by our actual enthalpy, which we don't know right now. This is what we're going to try and solve for, minus our low enthalpy, which is 3, which equates to our enthalpy at our low temperature, so 3,701.7. And we're going to make that equal to 700 minus 600, our high temp minus low temp, over 3,925.9 minus 3,701.7. That's our high enthalpy minus our low enthalpy. So what you can kind of think of this as saying is that if you can think of a straight line as you're increasing, if you have if we were to draw a chart of temperature versus enthalpy, and we had a straight line going from a low to a high, then the one for our state would be along that line, which means the slopes would be the same. And that's what we're saying here. We're saying the slope of this, the rate of change here is the same. And because that rate of change is going to be the same, we should be able to determine how far along between the low enthalpy to the high enthalpy we are. So if you solve this relationship on the right side for enthalpy, what you get is 3,724.12. Now we'll have more work problems you can do to practice this. We'll practice these in class because being able to use these tables is critical. But again, make sure you tab your text 4-8 and 4-9 and try and work on some of these on your own.